Hello everyone, starting again. I'm Sandhya Narayan from Verizon. I'm here at ON.Lab. I'm a member of the ONOS use case steering team and will be arranging presentations on ONOS use cases. This is the first of the series today, and if you have other topics or if you want to present, please contact me later. It's really exciting that NTT Communications has decided to do a field trial of a disruptive packet optical network based on ONOS. Today we have with us Marc from ON.Lab, who is the lead on the packet optical work, and Toru from NTT Communications, who is going to talk about their deployment plans. Marc, Toru, thank you for agreeing to present today, and I think we should get started.
Okay.
So, people out there, can you all hear me? And Marc?
Yeah, we hear you, Sandhya.
Thank
okay,
you.
Perfect, thank you. So good morning, everyone. A few things before we get started. Please mute your microphone when you join. There's too many people online here to get in an echo kind of party. The second thing I wanted to say is I'd like to thank the TST for this opportunity. We appreciate always in getting exposure for our work, and I think what we're doing is very important. Definitely demonstrated by the belief some of the carriers have put in us. So we will try to do our best as we can. Then a third remark is that if you have questions, I truly welcome them and I encourage you to make them. But I would like you to put them in the chat box, if at all possible. And at every 5 or 10 minutes, we'll stop and review if there's any burning questions that need to be answered. So with that, I think it's time to get started. So as you know, ONOS has a bunch of use cases. I think the most well-known is CORD by now, but there's a few others that we believe have a lot of potential in bringing innovation and efficiency into carrier networks nowadays. And the biggest one, at least is the one that I'm involved with, is the packet optical one. And as you see, it's a fairly long title up here, but there's really a couple of keywords that I want to take note of. The first one is multi-layer. We really believe in this kind of converged view of networking space, where we step away from the kind of silos. Oh, we have a packet network and we that independently of the optical network. No, we believe we should, bring a kind of converged, holistic view, if you will, to the table. The second keyword here is open. As you know, I work at the network lab, so it's pretty obvious I subscribe to that cause. Openness, as you'll see in the slide deck, relates to a couple of things. It has to do with how devices talk to the controller. It has to do with what kind of APIs the controller is exposing. There's various pieces that we believe should be open and ultimately lead to some kind of solution. Okay, with that said, let's quickly review the agenda for today. First, I would like to talk to you a little bit about the context and problem statement. This is very high-level stuff of why converged multi-layer networks are important and why we should be doing this. I don't think I will be telling any new things here, but it's important to set the context and to manage the expectations for the audience. Secondly, we'll talk about the ONOS platform. What is there today? What do we have? Right? What does it look like? What does the architecture look like? What are the pieces that are significant for the packet optical stuff? How does it scale? Then thirdly, we'll talk about some of the demonstrations we've done in the past, and they give an idea of what the current state of the work is, how we see the future in terms of the capabilities and the features and the scale that we're at. And then finally, the next point is really the core of this talk, I believe, is the exciting work we've done in the past weeks and months with NTT Communications to define and scope out the next proof of concept and their field trial. As you'll see, the NTT has subscribes to many of our beliefs around openness and converged multi-layer networking, and we're happy to assist them. And ultimately, since Open Networking Lab is really about an open source community, ultimately we hope that some members of the community, such as yourselves, can step up and bring pieces of the solutions to the table. And then finally, we wrap it up in a summary and open it up for more questions. So as I said, if there's any questions, please type them in the chat box. Santja will once in a while make a note of that or bring that to my attention, and then we'll try our best to get some answers to you. Okay, let's talk about multi-layer networks and how things are done today. Right, this is a kind of a picture of, I think we got it from ATI, that represents their kind of core national backbone. As you see, major cities all throughout the U.S., a bit more dense on the coast as to be expected. But all in all, fairly big-sized network that forms the core, the optical backbone, if you wish, of their network. The technology that is used there is what we call ROADMs. It's reconfigurable optical add-drop multiplexer. It's a type of optical switch, essentially. It does not understand what a packet is, but it does understand what a light is and what a wavelength looks like, and so on. And ultimately, in terms of scale, this would mean that tens to hundreds of wavelengths per ROADM are typically carried to the network. So on top of that, and this is very common in service providers network, there's a layer on top, and that's where the packet layer lies. Again, the topology, I don't want to fix myself too much on a specific topology. This is just an example where we show the IP routers not being available in every major location where we do have optical switching capacity. It could be the other way around. The point is that there's multiple layers of these networks, and on top of that, they start building services, they start building tunnels to create, kind of end-to-end connectivity and layer these things on top. Okay. So with that said, you'll see this kind of mapping process if at the very highest layer you want to set up some kind of tunnel. This gets mapped into respective buckets, into respective connections on lower layers. Now, this mapping process is exactly what the source of the problem, especially when you consider that every single one of those layers is typically operated and managed by a different kind of business unit within the service provider. So what that means is, in this mapping process, for example, if you want a connection between, say, A and C, and typically, the customer comes along and he does not know exactly how much he wants, somewhere in the range of 50 to 100 gig, right? That flexibility that is so prevalent in the service layer, where people, either cannot guess or estimate exactly what they need, or there's a lot of variability, is not as well supported on lower layers, and especially on the optical layer, which is very rigid and kind of coarsely granular, where there's only certain increments of capacity available, 10, 40, 100, 400, and so on. And now, obviously, there's a lot of research going on around flex grid and variable transponders. But all of this is still in its, kind of infancy and very hard to pull off in real life. So this kind of mismatch between the different layers is there, along with misunderstanding or lack of communication between different business units that manage these different layers, leads to a lot of problems with a multi-layer network without a converged control plane. Okay, so there's some animation here that goes on, which shows you how over provisioning is another, just put some more pressure on a system that is already under a lot of pressure. If you want to do protection, well, obviously you're going to have even more loss, even more capacity that is mismatched between the service layers and the actual transport. Okay, so the static provisioning and the multi-layer aspects of things really make things very tricky to get right. Now, what's the conceptual solution? Well, we're definitely not the first one to propose this. It's a kind of converged control. People have been talking about this for a long time. Think of GMPLS, think of other solutions. We believe with SDN Control that gives you the scale like ONOS does, and the logically centralized view of the network. We believe this is the right way forward, and this can actually solve the problem once and for all. Okay, so what you see here is a kind of screenshot of how ONOS looks at the world. There's only two layers shown here. The bottom is the ROADM layer, the top one is the packet layer. Obviously, you can think of situations where there's more layers on top or in between these kind of things. It's very easy to imagine, in the optical network, fiber switching, we've already demonstrated with ONOS. We can do this kind of optical cross-connect. WDM, the wavelength kind of routed layer. OTN, when you start doing grooming and multiplexing. Again, something that is well supported in ONOS, thanks to the community and some of our partners that have focused on these things. Same for packet layer. Well, there's more than IP. There's Ethernet. There's MPLS, kind of layer 2.5, if you will. There's multiple layers, and we have the primitives in place to support all of these layers very effectively, right? But the primitives themselves are not what matters. In the end, you need applications to really understand what this network looks like, and you'll see in ONOS, it comes with a bunch of applications. This has been growing at a very rapid pace. Again, thanks to our community that either deal with very specific layers, say the bandwidth calendaring only gives you optical connectivity in a calendaring kind of way. SDN IP is really focused on the packet layer, even though that one is actually being integrated with the optical network. There's a whole suite of applications that either focus on a specific layer or leverage some of the converged layer capabilities that ONOS offers. Okay, so are there any burning questions before I move on to the actual ONOS platform? No, we're good? Okay, so having said all of that, again, I don't think I've said anything very new or innovative at this time. How does ONOS, what does ONOS bring to solve some of these problems? I do understand some people may, have been exposed to this material. Please bear with me. Just 2-3 slides to set the stage of what ONOS is and the general architecture. Now, there's a few guidelines in everything that we do here at ON.Lab or within the community, by which we evaluate all the code submissions and all the, all the additions or contributions that are added. The first and foremost is the scale and the performance. So the high availability, scalability, and performance is, if you don't reach that kind of level of application development and so on, then it's not going to fly, or not going to become part of the ONOS platform. The second one is strong abstractions. I'll talk more about what kind of abstractions are important for packet optical, but they have to do with stepping away from a kind of very device-centric, hardware-centric worldview, and start thinking in terms of more abstracted ways. The intent framework is a very immediate example that many people understand as something that is, yes, this is a useful and valuable abstraction. Protocol and device behavior independence, very related to the previous one, but we can't build this thing for just a single vendor or for a single protocol. That should be very clear. So we have a very, it relates back to the abstraction, a very nice southbound abstraction of how to model devices, how to model their behavior, and any kind of device, any kind of protocol as you see fit. And the final one has to do with is more a kind of generic coding or software development goal. Is the separation of concerns and especially the modularity, being able to swap in and swap out certain pieces. If you don't like the way we've done our say netconf provider, well, sure, take it out and put in your own. That's all good, right? It relates back to many many different subsystems in ONOS, as we call them, are exposed as services. You can take them out and swap them in by whatever you feel is necessary. Okay. So quick overview of the ONOS distributed architecture. So just to how to read this kind of a diagram. At the very bottom, you have your hardware, your switches, and then on top of that, you have your controller instances. So ONOS is by design a distributed architecture. It's typically deployed as a cluster-based distributed system. So every one of those red boxes is essentially an ONOS instance. And the interesting thing here is that every instance is essentially identical. So it's the same code, the same kind of, the same stack, the same applications, the same core is available in every single instance. Now, obviously, the challenge is making sure that every instance has, uses the same kind of state, the same kind of state information, and synchronizing that is essentially the biggest challenge in our daily life here at Open Networking Lab. So, what does it bring you, this distributed architecture? Well, obviously, it allows you to scale out. You can add more instances to it. It allows you to be resilient to failures. If one of those instances goes down for whatever reason, and you might say, oh, this will never happen. My code is perfect, but it will happen, right? Because of code or hardware or something else or a combination. But if one of those instances or more instances go down, then you'll still be assured of a functional system. Now, as I mentioned, every single instance has identical codes. But another way of looking at this is that we layer kind of functionalities, if you will, onto every instance. So at the very middle sits the distributed core. That is exactly the thing that is responsible for the state management, notifications, and so on, right? Now, below that sits the abstraction that we call the Southbound Core API, right? That essentially tells you, okay, this is if you want to create a new device, this is the kind of functionality it should expose. It should report, hey, the device is there. It should report the ports it has, and so on and so on. There's a bunch of expected behaviors from every individual device in the network. And those devices, we talk to them using providers, which is essentially a piece of software that relies on a protocol to talk to the actual device, to generate the XML that gets pushed over netconf, to generate the open flow messages that are needed to do whatever you need to do with these devices. Now on top, and this is the more visible abstraction, as I mentioned, is the northbound core API. There's a bunch of northbounds that ONOS exposes. I guess the most famous one is the intent framework, but there's also a topology API. There's a flow objective API, which is a kind of abstraction of more simple or more lower layer flow rules. There's a bunch of northbounds that make sense there and that get used in many cases by the different apps that are ultimately where the true value sits and where the true functionality gets implemented. Okay, so this is a different way of looking at things. I'm not a fan of these kind of diagrams because it looks like, wow, these guys have been busy, but at the same time, people don't really know what's here. I think the only thing I wanted to mention here is that in terms of subsystems, in terms of core subsystems, there's really two types. One, the one that is highlighted now in gray, are the kind of subsystems that have to do with ONOS core functionality, the messaging, the events, how to register applications, leadership services, and so on. Whereas the right-hand side are the more networking-related subsystems, and typically of more interest to application developers. I'm saying more, not exclusively, but typically, application developers are interested in, okay, how do I fetch the topology? How do I program a device with flow rules? What's an intent, and so on and so on. Okay. Okay. So let's focus a little bit on the building blocks in ONOS that are specifically related to the packet optical stuff, right? So there's a bunch of applications, and I'm not going to spend too much time describing them because I think, in the rest of the presentation, you'll see bits and pieces pop up of these applications. But there's a bunch of applications that we wrote to kind of demonstrate the power and functionality the ONOS platform brings. I mentioned the bandwidth on demand, the calendaring, restoration. We can do very effective and very simple optical restoration. One of the highlights of the collaboration with NTT is that we're also going to include optical what's it called? Protection. Sorry. So to have a kind of autonomous behavior from the devices. Is there a question? I guess not. Okay. These are kind of high-level, kind of network-related functions. We also demonstrated things that are more lower layer, power balancing, fault management, and correlation. Things have more to do with, when we disaggregate hardware, how do we deal with certain features that are typically built into the box. In terms of abstractions, and again, these are the things that the application developers typically are most interested in. There's really two abstractions that helped us a lot in building some of these applications. The intent framework, obviously, we had to make some additions to it to support properly the optical stuff. But the intent framework, together with the converged topology graph, which essentially tells you you expose the topology as a simple collapsed graph. So there's no notion in the graph. Sorry, there's a notion, but the graph is collapsed. So packet and optical layers are exposed as a single graph. There is a notion in the sense that we annotate devices so we can still figure out, hey, if we want to have two separate layers, if we want to have split out the packet and optical layers, we can do that. But by default, it comes up as a collapsed graph, which allows you to be very effective in routing and in resource assignment and so on. It allows you to be very, very optimal since you have that unified converged view. But these two abstractions are really what allowed us to write in a way very simple applications that demonstrate very, very powerful features that up to now I have not seen very often in the field. Things are changing obviously, but this was very difficult to pull off in the past. In terms of core, obviously the scale and high availability is what drives all of this work. The noteworthy pieces here is the modular PCE. So ONOS comes with a path computation element, which is, in all honesty, very simple, very basic. But what it does allow is to, as I said, swap it out and pull in a new path computation element as you want. It's very typical for definitely big service providers and also many vendors. They have been developing their own PC solutions over the past years, I would say. So they have very advanced pieces of software there. So we're not forcing them to use ours. We give everyone the opportunity to bring their own, essentially. The other piece is the optical information model. So we spend a lot of time talking or exchanging ideas with some of the standardization organizations to figure out, okay, what is the optical information model? How should we represent a ROADM? How do we represent a wavelength, and all of these things in the distributed core inside of ONOS, such that it is at the same time very powerful, but still allows us to scale and offer high availability. And the third piece that is very important here is we have a very generic resource manager. So resources essentially are finite things, right? Things like spectrum in the grid, whether it's flex or fixed. Things like VLAN tags, MPLS labels. These kind of things are finite resources. So we built from the API side, from the how to use it side, the resource manager is very simple but very powerful, and allows us to scale to very large sizes of networks. And then I'll review some of these more when we hit later pieces or sections in the slide deck. But in terms of southbound, many people have the I think flawed assumption that ONOS is really OpenFlow based, and that is not at all the case, right? The southbounds I mentioned here only have to do with the packet optical stuff, right? There's many other southbounds that we support that people have been working on in the context of various projects, but there's a bunch of closed source southbounds that have been built. The TL1s are the most notable of these. Obviously, we support OpenFlow, NetConf-Yang. That is, we're making a lot of progress there. SNMP, we built a REST provider. There's many different southbounds that have been built or are in progress. Right. Okay. So actually, before I move on here, one of the things that is in progress is the work that was launched last year by AT&T. Is the OpenROADM concept. So as you know, OpenROADM is really about, well, there's a couple of pieces to it. One has to do with data plane interoperability. It kind of sets the parameters. Sorry, whoever just joined, could you mute yourself, please? Okay, so one of the pieces in OpenROADM has to do with data plane interoperability. It sets, the parameter space in terms of power and dispersion and so on among different vendors, the FEC and these kind of things, to ensure data plane interoperability. So Sienna box or transponder can talk to Fujitsu and so on. I guess that's a very topic, and many people have doubts in where this should be going, because obviously to achieve interoperability, I think it's well known now that they've taken kind of a step back from the state of the art, right? Obviously, the state of the art is not a lot of incentive from the different vendors to share or to exchange certain of these parameters or design parameters. But there's other pieces to it that are very important, I believe, at least from a network controller. And so single, multi-wavelength and services. Ultimately, this boils down to, from a network control, there's a southbound and there's a northbound for OpenROADM, right? As of now, I'm actually writing the northbound, the service API for OpenROADM, and adding support for that in ONOS. So consider it just another way of interacting with the optical network. We already can do, we already support our rules if you want to directly program devices. We support the intent if you want to use that. Well, we'll also support OpenROADM API if you want to interact in that way with the network. On the southbound, things are a little trickier because it's very hard to get our hands onto any kind of devices right now. So this is one of those pieces where we hope the community will step up and contribute pieces or the whole thing for Open ROADM southbound. Okay. All in all, I mean, I think there's a very good alignment. This is the first thing we noticed when Open ROADM was released, between ONOS and Open ROADM. And the most important thing is the functional decomposition. I'll talk later a little bit about disaggregated ROADM that we've built, and many of those ideas seemed in the end to work out or correspond to models proposed by Open ROADM. So, you know, in a way, we kind of were lucky, I guess. Okay, so anyway, this kind of concludes the kind of dry material of the platform and the context and problem statement. Are there any burning questions that we can handle right now? No?
Nothing on the chat.
Very good. So right now I'll move on to the demonstrations. These are some of the demonstrations we've done in the past 2-3 years. I remember ONOS was launched, what is it, 3 years ago? 2.5 to
December 2014.
December 2014. I think these demonstrations are nice data points of how much progress we've made in a short period of time. After that, I think the ultimate demonstration will be deploying these things in the field, and we'll have Toru talk a bit more about that. So in terms of demonstrations, we've really done 3 things, I believe, we should mention. First one was in last year, the summer of 2015, where we showed a multi-layer, multi-vendor solution. What you see here is at the very top we have an ONOS cluster, an ONOS cluster instance that was by the way based in California. All right. This cluster was essentially controlling 3 different vendor domains. All right. We had the first domain, which was based on Sienna and Corsa equipment. A second domain in a different location, by the way. So the first one is in Canada, the second one was in Texas. The second domain, Fujitsu and Corsa. And then the third domain was again in Texas, but again in a different location with Huawei packet and optical layers. One important thing to note here is that and I mentioned or alluded to it previously, it's very hard to achieve data plane interoperability. Very hard, well, let's say impossible. So none of these domains have data plane interconnectivity, right? They are connected on the control plane to ONOS, but not on the data plane, right? And then you know, what we did is as I said, we have this very nice abstraction on the southbound of how devices should behave and look like. And so we went to work with some of these vendors and wrote the various drivers, plugins, if you will, to allow us to talk to the various devices. So we used OpenFlow for the Corsas, we used TL1 for the Sienna and Fujitsu ROADMs, and we used PSAP for the equipment. All of this plugged in very neatly into ONOS and allowed us, and this is really the biggest, you know, innovation in this demo. It allowed us to write a single application that was able to drive traffic in the different vendor domains. So you develop the application, the business logic, if you will, a single time, and that allows you to support any kind of domain, any kind of technology, any kind of vendor. And so the kind of applications we showed was on-demand optical bandwidth. We demonstrated multi-layer restoration, and we demonstrated certain optimizations in the multi-layer networking. So optimizing how IP traffic streams used or reused existing optical connections. Okay. By the way, after this talk, I believe we can share these slides. There's a link here if you want. We recorded the demo and a video of it. So if you want, please take a look and give us your feedback. Same is, by the way, valid for the next one I'll discuss, which was earlier this year in the spring of 2016, where we showed a different kind of a different setup, if you will. So the services become more, you know, more reminiscent of the of actual deployments. So we built our own WDM network, and you see the rack here. I'll discuss it in a bit what it really means, this rack, and demonstrate layer 2 VPN connectivity over that, right? All in an integrated fashion. So we had a nice UI to say, hey, I want to connect these 2 data points while requesting that layer 2 VPN, requesting that packet layer connection, automatically generated the instructions to set up the optical and packet layer flow rules. So it's kind of very nice converged view and operation of the network. Okay, so I lost my mouse. Yes, here we go. Okay, so about that rack that I just showed, let me just go back. This thing, what you see here really is a 3 nodes optical network. So there's a first node here at the bottom with that big white box. I'll tell you in a minute what that is. There's a second node here in the middle, and then a third node at the very top. All of these are 3 ROADMs. It's a 3 node ROADM network. Now, the way this works is we kind of figured that in the spirit of openness, we had a lot of trouble supporting any kind of meaningful optical equipment, in that, you know, everything that is out there right now is driven by closed interfaces, right? I mentioned TL1. Sometimes there's a netconf-yang, but then still that's kind of proprietary. There's not a lot of open interfaces to talk to optical devices out there. That was one of the drivers to start and try to create our own optical devices. All right. And so the way this works is, typically if you go out to a vendor nowadays and you ask for optical equipment, well, you can get this kind of giant vertically integrated box, right? It has everything. It has a chassis, it has slots, it has shelves, it has pluggables. They all come from kind of the same vendor, the same supplier, right? Now we ask the question, hey, can we move away from that model and mimic the kind of white box revolution, I call, that is going on in the data center space, right? Where you also used to have these, you know, integrated top of rack and core switches that had everything built in. While now you see more and more these are, you know, replaced by simplified data center white box switches. They have basically nothing except switching hardware. Everything else, the software, is something you can put on there, mix and match, choose whichever pieces of protocol you want, or what kind of control plane you want, the network OS, and so on. So there's a bunch of, obviously, pros and cons to this kind of approach. I guess the vendor lock-in is very obvious. The one-size-fits-all is another obvious one. You know, with a kind of disaggregated model, you can right-size your equipment, right? Get only the equipment you need and not what the vendor has on offer, right? Which is typically kind of small, medium, large, and that's it. Make your choice. The forklift upgrade, if you want to upgrade certain pieces of this kind of optical device, well, in the disaggregated model, you can swap out just a transponder and keep everything else in place. That is typically impossible in the current vertically integrated world. Now, the big question, as I said, there's pros and cons, is in terms of integration, right, and in terms of performance. The vertical integration, you know, there is value there. People have spent time in making sure all the parameters are tuned properly, all the power levels are set, and so on and so on. So the question is, in a disaggregated model, can we still do that using software-driven integration? It's my personal belief we can do that, but this is, as of yet, an unproven theory. Okay. So the way this works, and this kind of relates back to the picture of the rack I just showed you, is where we break it down into kind of 3 components. A ROADM consists of 3 components in our view. One is WSSs. These are the wavelength selective switch. It's the switching capability, right? The second one is the transponders or muxponders, depending on their capability. But essentially the thing that takes in packets, client-side signals, and generates a line-side signal, generates a wavelength. The third thing is what we call the backplane. You could consider this optional equipment in that the backplane ensures we can connect the transponders to the WSSs in the proper way. You can do this manually, but to use something like the box I just showed you, that giant white box, this thing here, which is a kind of cross connect, a fiber switch, or you can also use there's different technologies to realize this kind of function. It allows you to have a kind of programmable backplane. It allows you to reconfigure your ROADM on the fly. Okay, and then on top of that, obviously, because of this removal of the vertical integration, some of the functions need to be put into either a device controller or a network controller that have to do with alarm handling and have to do with power management. Maybe also the protection, the autonomous decisions, how to configure all of that, have to become part of a software layer on top of that. These are, by the way, some of the partners that we worked with in realizing this. You'll see many of the famous names in the industry, and we were very happy to pull this off. Okay, so there's, by the way, some work in progress right now. Some are going better than others, but they are definitely still on track. Have to do with making more data points available and showing that ONOS can drive actual production traffic and production networks, especially on the optical layer. One is in Europe, the other one in Korea. The motivation, again, as I said, is really demonstrating that we can do this. These are, by the way, research and education networks. I think the work that we're doing with NTT will propel this kind of activity in the next phase. And that's really what we want to try and achieve. Okay, so with that, I think I've said everything I wanted to say. And my apologies for talking so much. But we now arrived at the piece where my colleague Toru will discuss the next proof of concept and some of the requirements and design for the field trials by NTT Communications.
There is a question.
Oh, there is a question? Okay, let me first handle. So I'm not quite sure if you mean on the data plane or on the control plane, but let me just try to answer. The way we've done it so far, and that was really because we had to, it's kind of a pragmatic solution. In terms of control, everything, every device came with their own control protocol, right? So you'll see here, OpenFlow, we used OpenFlow for the uplink ROADMs. We used REST for the Sienna wave server transponder. Every single one came with their own protocol, and that in itself is not a problem. We've demonstrated on multiple occasions ONOS can easily handle different control protocols. Now, in terms of communication between the different pieces, so let me make it very clear that there are no kind of control loops, no control feedback loops existing in this kind of solution, right? I don't think there should be, right? If we can, intelligently go to the controller when we need to, and everything else we do in a kind of autonomous way, have the device make its own decision, I think we're in good shape. So the other piece of that is, I think, in terms of data plane connectivity. So say a wavelength comes in here, packets come in here, goes through transponder, generates a wavelength, goes to WSS, and goes to the line side. So there, what we did is we had a very simple power management application in ONOS that set the various power levels on the transponders and on the ports, the attenuations, and so on. Now, in all honesty, so that was kind of statically configured based on some calculations we did offline, statically, essentially. Now, nothing prevents us, because some of this work allowed us, we've opened up the APIs, and how to talk to these devices, how to set these attenuations, and so on. So nothing stops you now from writing a more dynamic power management application. Obviously, this is tricky to get right because of feedback and all of that, but it's definitely doable. I'm sure with the this logically centralized view that a network controller brings, this is definitely within the cards to do this effectively. I hope this answered the question. Anything else on the? No? Okay. So with that, let's move on to Toru's.
Hi, this is Toru from NTT Communications. So from this part, I will show our next POC plan and our NTT Communications and deployment field trial plan. So first, let me explain our expectation for ONOS project and ONOS controller. So we, NTT Communications, are intended to transform our wide area transport network operation with disaggregated transport network and ONOS controller. So with disaggregated transport network, we are aiming to achieve the agility and cost reduction. So combining the minimum component of the transport network make it possible to create new functions and network services more rapidly with lower CapEx. Also, CapEx and OpEx reduction can be realized by using a multi-vendor component other commodity devices. And we have three expectations for our project and controller. The first one is community influence. So the POC of disaggregated ROADM and its controller has been successfully developed through the packet optical case and equal project. So in ON.Lab. So we believe that that was the first trial of making kind of optical white box and its controller, and ON.Lab is still leading the industry trend of disaggregation of carrier transport network. And second one is cost reduction of controller by using an open source controller. So, and the third one is related to the architecture of ONOS. So we expect the programmability of northbound application on top of ONOS. Network model and intent framework and so on. Common framework and northbound API. And we think that the first one is community influence is the most important part, and we really want to realize the commercial service deployment of disaggregated transport network in the future with this ON.Lab community, ONOS community. And to realize the commercial service deployment of disaggregated transport network and ONOS, so this is what we envision the long-term plan for the commercial deployment. So in 2016, in this year, ON.Lab and our partner and collaborators successfully have developed and shown the POC demonstration of disaggregated ROADM in the ECO project and packet optical use-case project. And we showed the POC at the ONS and OFC this year. Also, some vendors say that they released the first kind of disaggregated ROADM product this year. And next year, and next year, we expect that the disaggregated ROADM product vendors will increase, and some vendors will release the disaggregated packet transport products such as defense switch and API router and so on. And to accelerate this market trend of disaggregated transport network, we want to we plan the next POC activity on packet optical use case project in ON.Lab. Also, we NTT Communications plan the field trial of a disaggregated transport network in our wide area testbed network around Tokyo. So I have the detail over later. And after that, in 2018, so we expect that disaggregated transport network will become common, and the commoditization of disaggregated transport will start. And through the continuous development of ONOS and its successful next POC, we believe ONOS will be the de facto open source controller for the disaggregated transport control. And in parallel, we and Comm are going to make some decision of commercial service deployment from the both perspective of technical aspect and business aspect. And toward the commercial deployment of disaggregated transport network, we think we need some additional functions and also performance and stability testing evaluation. So regarding the functions, for example, we need some protection switching function for both packet layer and optical layer network. That realizes automatic circuit switching within the 50 milliseconds. And also we need some functions like a monitoring and alarm handling functions, and more. Also we need some more open interface, such as the open ROADM interfaces and so on. And to develop those additional functions, we plan next POC development. We have a next POC development in ON.Lab. So and also for performance stability evaluation, we NTT Communications field trial through the deployment, and we will feedback the results to the ONOS community. And this is our current development roadmap. So currently we are developing the open ROADM interfaces and protection mechanism and so on. And also we are going to develop some additional functions such as monitoring, alarm handling, and also we are going to develop some layered intent and transaction rollback mechanisms and so on. So for the next POC, we do actually call for the contributions for the next POC in ON.Lab. So first, on software development contributions are very welcome. So we will develop these functions such as the open source device driver and protection mechanism and so on, monitoring subsystems, the intent. So to develop these functions, excuse me. So we will develop this function along the development roadmap in the previous slide. And second, device and facility contributions are also very welcome to build a disaggregated transport network pod in ON.Lab. So and our demonstration target will be OFC in March next year and ONS in April also of next year. So please let us know if you have any interest to work with us in this next POC.
So you want the community to work with you on all
yes,
these?
Yes, exactly right. Yes.
Okay.
And finally, let me show our NTT Communications field trial plan. So toward the commercial deployment, now we are planning the field trial of disaggregated transport network with ONOS in detail. So currently, at first, as a step one, we are going to deploy a few disaggregated transport network devices and ONOS into our wide area testbed network around Tokyo, like this picture. And also, we will evaluate the implementation status of the basic functions for disaggregated transport network control in ONOS. And we will evaluate this by March next year. And after the evaluation, we will feedback the results and additional required features to the ONOS community to plan next development roadmap of ONOS. And after that, if the step one is successful, from next year, from April of next year, we are thinking of planning to start on step two of our field trial. So after the deployment, we we will continue the operation of disaggregated transport network and ONOS in our wide area testbed environment, and to evaluate the performance and stability of these devices in ONOS control. And through the step 2, we will evaluate ONOS in detail from the both multiple views, functions, performance, and reliability, and so on. And after that, if the step 2 is successful, we will start the step 3. So currently we are considering to integrate the disaggregated transport network with our existing commercial network environment and evaluate the feasibility of commercial service deployment from the view of both technical aspects and business aspects. So at this moment, we are planning the detailed field trial plan now. So we will show the detailed plan to the ONOS community as soon as possible this year. So please let us continue to discuss and collaborate with this POC and trial together. So,
You're going to summarize?
Yeah. Yeah. So finally, let me summarize presentation. So we showed.
Okay. So I guess the summary is as follows. The words speak for themselves, but ONOS is ready as a controller for converged multi-layer networking. We've done many, we have collected many data points so far that this is the case, identified many gaps. The community in all of this is growing at a tremendous pace, and we hope we can keep on relying on some of the amazing work you guys have contributed. And we feel this thing is production ready. We see some of the research and education networks stepping up to deploy it in production traffic. We see service providers, major service providers doing the same, and we can only hope many others will join this party. So with that, I thank you very much. Me and Toru are very thankful for this opportunity again. We'd like to open it up for questions. If there's anything we can help you out with, we'd be happy to do that. Thanks very much.
Thanks, Marc and Toru. There is one question here from, it says, how is interoperability between ONOS applications ensured, especially multiple applications trying to secure bandwidth for their own requirements?
Yeah, that's a great question. So there's various different pieces. I guess the fact that ONOS comes with different APIs is actually kind of a source for this kind of problem, right? I can assure you that if you stick to single API, say you use the intent API, there are built-in features to ensure there's no contention or the resource management piece of things is done properly. If, on the other hand, you have various applications, one that is directly programming devices and bypassing, for example, the resource manager, and the other one does do things properly and goes through certain pieces, then yes, you might run into problems. It's the same in a Linux operating system. If someone starts overriding the memory and does not care about virtual memory, well then you're going to end up in trouble, right? So with good design, I would say you can sidestep or avoid many of these problems.
Does that answer your question?
Yes, it does. Thanks.
Okay. There's another one.
Yeah, I see on the chat window there's a question on the plan to integrate packet optical use case and the court use case. So we specifically chose to develop these things as separate use cases because they focus on very different locations in the network. Court really focuses on the central office, Packet optical is typically a WAN or transport or metro kind of thing. Now, nothing stops you from running cord and having an ONOS controller, packet optical controller driving the transport network, right? So nothing stops you from doing that nowadays. In terms of, genuine integration, it really depends on how far you want to take this. But I guess, the hopeful news here is that all the APIs that we developed, that's really the powerful story that we have here. All the APIs are open, right? So if you want the cord controller to talk to a transport controller, you can start doing that today.
Thank you, Marc. Any other questions? You don't have to put it in the chat window. You can call in. You can please call in and talk to us directly. Okay. Looks like we do not have any other questions. So.
No questions for Toru and the NTT deployment?
So what devices are you planning to use, Toru?
So currently, for the step 1 of our field trial, we are preparing this. We are going to deploy the 150 devices and ONOS controller into our network. But after that, for the step 2, we are thinking of using multi-vendor disaggregated ROADM series and disaggregated transponder series from multi-vendors.
So are you doing this comparison with other SDN controllers that's happening in parallel?
Yes, also we are evaluating some other SDN controllers for disaggregated transponder as well as ONOS.
Will you be sharing those results too with all of us?
Unfortunately, that's all of the yes, we are able to share the results.
Okay.
That will be very useful in the sense that if there's something you really like about another controller, we can try to build that feature as well on us,
Yeah, that will be very useful feedback. Thank you all for joining this call, and if you have questions later or any feedback, please send them to me or Marc or Toru, and we'll see how to get those answered.
Thank you.
Thank you.
Thank you.
Yeah.
Bye.